Hello and welcome to Section 8, where we'll be discussing the terrestrial planets and their properties and features. To start ourselves off, we have this excellent picture from Astronomy Picture of the Day, where we can see 6 planets. Now, this is all just a bad joke. We'll see Mars, Saturn, Jupiter are the first 3, and then the reflections in the water are the other 3, getting us to 6 planets in the picture. Hardy har, I know. Bad jokes, but what are we going to do? In this section, we're going to discuss the effects of impacts on the shaping, the surface features of these terrestrial planets, and talk about the radiometric dating to figure out the ages and how the heck that works. And then we'll probe the interior of these planets, figure out how we can use different types of waves to figure out what's going on. Talk about tectonism and the related volcanism that's happening, predominantly on Earth, but we see these features on other terrestrial objects. And at the end, summarize what we know about the water. Where do we find water on the terrestrial rocks? So to define what we mean by terrestrial planets, we're going to say that the terrestrial planets are anything that's primarily composed of silicates, rocks, or metals. And our discussion mainly is going to apply to Mercury, Venus, Earth, and Mars. Some aspects of this will apply to the moon. We'll understand that in later sections about the origin of the moon. We say that the terrestrial planets are composed of refractory materials. So when we mean by refractory, get your idea of, yes, the silicate, rocks, or metals, but formally, when we say refractory materials, we're saying that these are materials that do not change their physical state under wide ranges of heats, pressures, or even chemicals dripping on top of them. The surface layers might interact a little bit chemically, but the entire substance itself will remain relatively stable and solid. And that's where we get this idea of these terrestrial rocky planets. In this chart we have here, we are comparing different aspects of the terrestrial objects. So let's look at Earth. Earth is 1 astronomical unit away from the Sun. And Mars is 1.5, Venus 0.72. And let's see what else we can see. Let's talk about masses here. Comparisons I like to see. All right. Earth and Venus. Earth has a mass of, our units here, 1 Earth mass. Venus is about 80% the mass of Earth. The diameters, not too different. Right? Earth is a little bit bigger than Venus. Now for the interesting ones. Let's look at the sidereal rotational period, focusing on Venus and Earth again. Earth, obviously, we all know what our sidereal rotation period is. That's an Earth day, about 24 hours. A little bit more accurate too. Sorry, taking account for the minutes. But let's look at Venus. 243 days, 243.02 Earth days for Venus to rotate once around. So what is that? What's causing that? Well, it turns out that's going to be because of this obliquities. Now, our next slide will actually figure out what these obliquities are. You should recognize this one, 23.45. Well, that's the tilt, the obliqual tilt of Earth relative to the Sun. Venus has this 177.36 degree tilt. Let's look at what that means. This idea of obliquity is to define it, it is the difference, the tilt between the rotational axis and its orbital axis. So the red line represents the orbital axis. In this perspective, every planet would be going into the screen right now as they rotate around the Sun. Now you have these obliquities, these tilts. Earth, are ever so infamous 23 degrees. Remember the reasons for our seasons. Look at, say, a planet like Uranus that has this 97 degree tilt. Remember how our seasons are a product of this tilt? Well, Uranus is going to have a very interesting, stranger seasons than what you see on Earth. And we'll save that discussion for a future video. Coming back to Venus, that 177 degree tilt, what does that mean? Well, look at the direction of rotation. Earth, in this picture, will be rotating, its sidereal rotation, the days, will be rotating this way. Venus is going the opposite direction, very slowly. It's a very slow rotation. What we think happened in Venus's early life is some cataclysmic event smashed into Venus, causing it to tilt over and start rotating the wrong direction. Go back to its sidereal period. Earth has about 1 day to rotate around, where Venus is, going back to this, remember, that 243-day tilt. So it has a very slow rotation. This is trying to conserve angular momentum. Some cataclysmic event hit Venus, flipped it upside down, and started to rotate in the wrong direction, but very slowly. Here's a wonderful animation showing those oblique rotational speeds, comparing the 8 planets. Notice how Venus has a very slow rotation compared to Earth or Mars. Now let's start talking about the surface features of these terrestrial planets, what's happening and what's shaping them. And for our terrestrial objects, we're going to describe by the end of this series the 4 processes here: impacts, tectonism, volcanism, and erosion, and how that shapes the features on the surfaces of these objects. Starting with the impacts, here's the picture depicting a cataclysmic event. Look at how far up these impacts can create, how far material can be ejected out into the atmosphere. So, things we know about impacts is that they can have extreme consequences. A single impact can change the entire atmosphere of a planet. And remember our pictures of Venus, possibly change how Venus rotates around, the direction it rotates. And in some hypotheses, even be so catastrophic, so gigantic, that it created the moon. So anytime an object falls from space and manages to not burn up in our atmosphere, will then cause an impact on the surface of the planets. So they'll leave behind what we call the impact craters, and that impact crater will cause a lot of material to become superheated. This will vaporize rocks in the area, it will melt things, and when that impact comes in, it will eject out a lot of secondary material. So the initial object crashes into the surface, melts this stuff, and creates this blowback of material flying up. Imagine filling a giant bathtub full of water and just dunking something in there very rapidly. The pool of water will splash out, but then some material will sploosh back in and fly into your face. Well, that secondary material will created by this ejecta will create secondary craters. And so all craters are described by these central impact regions. They'll have this crater wall, and around that you can see those secondary craters or rays of ejected material. And we see all the terrestrial objects have these indications of cratering. All the terrestrial objects have shown some sort of impact has happened on them. Here's a video demonstrating experiments trying to see what the impact cratering looks like. Take a high velocity object, and in this video, just smash into the sand, but you can see the particle ejected out, creating the secondary craters and rays. You can do experiments like this to comparisons. What type of craters do you see on the moons or other planets, and whether a hard object slammed into there, or what the surface features will look like. Is it gritty sand like this, or is it a harder, more rocky granite substance? Observations we can make on the different surfaces of the crater impacts can tell us a lot about the planets. For instance, here's the Barton crater on Venus, big, 50 kilometer in diameter. But look over all of Venus and Earth, and you're going to see relatively few craters compared to Mercury and the Moon, where there's going to be tons and tons of craters. Now Mars, this is an interesting one. So this would be the secondary craters. Here's your primary crater, and you see how it kind of slushes outwards. This is one of those indications that Mars was at some point in time a wetter, muddier planet, because this looks more like mud than rock being flung out there. Here's a false color image of the moon highlighting the wide range of impact craters and depth that you can see across the surface features. So the moon's not very geologically active, and because of that, the number of craters will just keep building up over time, and you could model the rate that the moon will get hit by a crater as being a relatively constant. So the number of impacts gives us an indicator of how old the surface of this surface is, how old it is. The more craters being there's, the longer it's been around. Now, obviously, this changes if there's any sort of tectonism or erosion, because that will work to smooth out the surfaces. Earth, it's probably getting impacted about the same amount as like the moon or any other planet, but because we have geological activity, it smooths things out.